Figuring out how I want to change my variables can be a little challenging on occasion, and I don't want to just guess at it. So I'm going to look at the region or the integrand for clues about the kind of change of variables I might want to make. So I'm first going to talk about using my integrand in order to help me choose the transformation I need. Now we can often encounter integrals that contain integrands that aren't simple to integrate, and we need to find a change of variables in order to proceed. I want to examine my challenging integrand for a clue about a change of variable that could be useful, and my goal is to keep things simple. So for example, if I have a double integral over a region R, and my integrand is the square root of the quantity 3x minus y over the quantity x plus 2y plus 4 dA. If I were to let u be 3x minus y and v be x plus 2y, so that x is equal to the quantity 2u plus v over 7 and y is equal to the quantity 3v minus u over 7, my Jacobian will become 8/49ths, and this will transform my integral into a double integral over s of 8/49 times the square root of u over v plus 4 du dv. This is a much simpler integral to evaluate. So let's work an example. I want to evaluate the given integral by choosing a change of variables based on the integrand itself, where r is the parallelogram bounded by y minus x is equal to 1, y minus x is equal to 2, y plus 2x is equal to 0, and y plus 2x is equal to 4. I'm evaluating the double integral over the region R of the quantity y minus x over y plus 2x plus 1 raised to the 4th power dA. I'm going to let u be y minus x and v be y plus 2x. I'm going to plot the boundaries of my region R, which gives me my parallelogram with a vertex at -1/3, 2/3, another vertex at -2/3, 4/3, a vertex at 2/3, 8/3, and a final vertex at 1, 2. This region can be transformed into a rectangle in the UV plane with vertices at 1, 0, 2, 0, 2, 4, and 1, 4. X is equal to v minus u divided by 3. Y is equal to 2u plus v divided by 3. The partial of x with respect to u is -1/3. The partial of x with respect to v is 1/3. The partial of y with respect to u is 2/3, and the partial of y with respect to v is 1/3. My Jacobian becomes the determinant of a 2 by 2 matrix with a first row populated by -1/3, 1/3, and the second row populated by 2/3, 1/3. This determinant becomes -1/3. So that my double integral over region R of the quantity y minus x divided by y plus 2x plus 1 raised to the 4th dA will become the iterated integral from 1 to 2 of the integral from 0 to 4 of 1/3 times the quantity u over v plus 1 raised to the 4th power dv du. Taking this from the inside out gives me 124 over 1125 times the integral from 1 to 2 of u to the 4th du, which gives me 124 over 1125 times 31 over 5, or 3,844 over 5,625. I may also want to examine the region to help me choose my transformation. If I let R be the region in the first quadrant, bounded by the parabolas y is equal to x squared, y is equal to x squared minus 4, y is equal to 9 minus x squared, and y is equal to 16 minus x squared, I can plot the region that is bounded by these four curves in quadrant 1 of the xy plane. When I examine the boundaries, I can write my equations in the following forms. Y minus x squared is equal to 0, y minus x squared is equal to -4, which I can interpret as y minus x squared is equal to a constant. I also get y plus x squared is equal to 9 and y plus x squared is equal to 16, which I can also interpret as y plus x squared is equal to a constant. So that my choice of change of variables will be to let u equal y minus x squared and v equal y plus x squared, so that u will go from -4 to 0 and v will go from 9 to 16. This gives me a rectangular region in the UV plane that is bounded on the right by the v-axis and on the left by the line u is equal to -4. On the bottom, it's bounded by the line v is equal to 9, and on the top by the line v is equal to 16. Now I have a region that is much easier to work with. So let's work an example. Let's examine the boundary of the region to make a change of variables and then evaluate the new integral for the double integral over r of the square root of the quantity y squared minus x squared dA, where the region R is the diamond bounded by y minus x is equal to 0, y minus x is equal to 2, y plus x is equal to 0, and y plus x is equal to 2. The first thing I want to do is plot my region R, showing the coordinates of the vertices at 0, 0, 1, 1, 0, 2, and -1, 1. I'm going to let u equal y minus x and v equal y plus x based on the boundary of my region that I was given. This will give me a square of area 2 in quadrant 1 with one vertex located at the origin in the UV plane. It also gives me x is equal to u minus v over 2 and y is equal to u plus v over 2. Now, using my equations for x and y, I find that the partial of x with respect to u is 1/2, the partial of x with respect to v is -1/2, the partial of y with respect to u is 1/2, and the partial of y with respect to v is 1/2. Therefore, my Jacobian becomes the determinant of a 2 by 2 matrix with the first row populated by 1/2, -1/2, and the second row populated by 1/2, 1/2. This gives me a determinant of 1/2. My double integral over region R of the square root of y squared minus x squared dA transforms to the iterated integral from 0 to 1 of the integral from 0 to 1 of 1/2 times the square root of the quantity u plus v squared over 4 minus u minus v squared over 4 du dv. This gives me the integral from 0 to 1 of the integral from 0 to 1 of 1/2 the square root of u times v du dv. I evaluate the innermost integral with respect to u, and I get the integral from 0 to 1 of 1/3 v to the 1/2 dv, which becomes 2/9. So now you get to try it. Pause the video and evaluate the given integral using your choice of change of variables. Sketch both regions S and R, and when you're ready, restart the video to check your understanding. You want to evaluate the double integral over the region R of e to the xy dA, where R is the region bounded by the hyperbolas xy is equal to 1 and xy is equal to 4, and the lines y over x is equal to 1 and y over x is equal to 3. In this case, I'm going to examine the boundary values of my region to see if I can come up with a change of variables that will work. The first thing I'm going to do is plot the region I've been given, which is a region bounded by the lines y is equal to x and y is equal to 3x, and by portions of the hyperbola in quadrant 1 bounded by xy is equal to 1 and xy is equal to 4. I'm going to let u equal x times y and v equal y over x. This means that x is equal to the square root of u over v and y is equal to the square root of u times v. The partial of x with respect to u becomes u to the -1/2 v to the -1/2 divided by 2. The partial of x with respect to v gives me negative u to the 1/2 v to the -3/2 over 2. The partial of y with respect to u gives me u to the -1/2 v to the 1/2 over 2. And the partial of y with respect to v gives me u to the 1/2 v to the -1/2 divided by 2. My Jacobian, when I compute the determinant of my 2 by 2 matrix, gives me 1 over 2v. Now I use my Jacobian and my substitution. My new limits of integration will be from 1 to 4 in u and 1 to 3 in v. The new region is a rectangle bounded by the lines u is equal to 1, u is equal to 4, v is equal to 1, and v is equal to 3. My double integral over the region R of e to the xy dA becomes the iterated integral from 1 to 4 of the integral from 1 to 3 of e to the u over 2v dv du. Integrating with respect to v, I get the natural log of 3 over 2 times the integral from 1 to 4 of e to the u du. This gives me the natural log of 3 over 2 times the quantity e to the 4 minus e. This is how I use my integrand or my boundary of my original region to help me decide on my change of variables in 2 dimensions. Be sure and let me know if you have any questions.